Hello, this is Erin O'Neill talking through problems 3, 4, and 5 of my lab 4. So let's see, what does 3 ask? I have it printed here. Okay, so use the frequency generator app and move the tube up and down until you get the loudest sound. Locate the spot with the shortest open straw or PVC length for the fundamental. Okay, so I found the fundamental for 3 different frequencies. I started with 1,000 hertz, and then 500 hertz and 300 hertz. And you can kind of see here, that I got a PVC pipe off the side of the street, and I cut it so that it would fit into this bucket, which I filled with water, and was measuring using a ruler how deep, or I guess how much was exposed to air that was not submerged while I played the tone through this headphone, which was directed into the pipe, and I listened carefully for the resonant frequencies, which was when it had the loudest tone noise. Luna, my dog here, Luna helped me. She's a great helper and also got in my way a lot, so shout out to Luna. And so first, when if I found these calculations by hand or also on Excel, I could figure out that the length, according to literature, if the temperature of the room, which my thermostat said it was 68 degrees, then the velocity of sound in air would be 343 meters a second. And so I took velocity over 4 times frequency, that's what the F is, 1,000 hertz, and what I calculated the length would be in perfect scenario is 8.57 centimeters. And so when I did it by hand in my trial, what I measured was pretty close, 8.40 centimeters. So I knew I was probably just, not in perfect conditions. Who knows what exactly. Maybe my bathtub was cooler than like the rest of my house. Hard to know exactly what was causing the difference there, but I was pretty happy with how close it was. So I kept going. My next frequency was 500 hertz. And so plugging that into the equation, I solved that it should be something close to 17.15 centimeters. And what I ended up getting was very close. This time I got 17.20 centimeters. And then finally for 300 hertz, again, I solved it for 28.58 centimeters and I measured 28.60 centimeters. So this was really close, which was neat. Okay, next page. So 4, use your measurement to compute the speed of sound in air. So, did I already talk about that? No, I just talked about the length. So the speed of sound, so you know that velocity equals the length times 4 times frequency, or frequency times lambda. And so in this case, I would plug in the length I measured and then multiply it by 4 times the tone or the frequency. And so each time I did this, I got roughly close to 343 meters a second. You can see 336, 344, 343.2, awfully close. And so, I was pretty close. And then to get the best velocity from your data, plot the frequency and the 1/4L, and find the best straight fit line. So I did that. The first time I went through and did this, I just had my numbers switch. Like I did 1,000, 500, 300. So anyways, earlier we had talked in before class, and I had a negative number. So when I redid it, I got a positive number. Anyway, so I just found the slope by taking these 2 points and dividing change in y over change in x, and my final velocity on average is 333.1 meters a second. And I can show you this in my Excel. So this was my frequencies, my lambdas, and 1 and 3 and 5. And then, yeah, what I did was I took at 1,000 hertz, where did this number come from? 1 divided by 4 times what I measured the length for 1,000 hertz. So I plugged this in, that in, got this, and solved for slope. And it's pretty accurate. It's pretty neat. I think that's all I have to talk through. So, yep, thanks, that's it.